All right, let me talk about something completely different. This is imaging with the radar. So you transmit relatively long pulses, and then you look at the time structure of the returning signal. So this is looking at a meteor or meteorite. Size is about a mile. So this is the raw data on this side. This is what the radar sees. And then over on this side, this is a sort of inversion to try and model what it really looks like. And this is actually the Comet nucleus that was visited by this EPOXI spacecraft. And so this observation, the thing is about a mile across on the long dimension, and it was 11 million miles away from Earth when this observation was made. And here's actually a picture of that Comet nucleus made by the spacecraft from about 400 miles away. And so that gives you some feel for the ability of the radar really to image those things, even at dramatic distances. And then I have a picture of another asteroid, actually of an asteroid. This is a much bigger thing. It's a couple of 100 kilometers by maybe 100 kilometers. So this is quite a substantial lump of rock, which was well known from optical astronomy, but was believed to be actually two lumps of rock going around close together. And the Arecibo modeling was able to demonstrate that to be consistent with the radar returns. Actually, this was something that looked much more like a dog bone and was connected together. Every time I look at that, I wonder if somebody's actually pulling our leg, and it really is. Anyway, and the radar is just preeminent in its ability to measure the orbital parameters of objects in space and see something about their surface and allow you to deduce something of the composition. And so it's in huge demand to actually look at known and also newly detected objects that may be in orbits that might intersect the Earth. So they're called near-Earth objects. And we have a contract running with NASA to run the facility at short notice when new things are discovered and determine their orbital parameters and determine whether they're going to hit us or not. I'm not sure what we should do if the answer is it's going to hit us. But anyway, there is nothing else that really that can do it with the speed and precision of Arecibo. Now I want to go back a little bit and talk about the incoherent scatter stuff that I started off talking about. This is the same sensitivity comparison that I showed you when I was talking about the size of the dish, except now this is on a log scale. So, here's the Millstone Hill incoherent scatter radar belonging to MIT over in Massachusetts. It's a 150-foot dish, so it's 3.2 to 4.85. That's the 40 times that I told you compared to the big dish. So Arecibo is way, way more sensitive than any other incoherent scatter radar that we have on the planet, and that gives it the possibility to do things that they can't do. So here's a confusogram where here's relative frequency from the center frequency of the radar, so out to some numbers of megahertz on either side. And this is the time of day. So this is night down here. And then as the sun comes up, you begin to see all these other features in the spectrum. If I did that same thing at one of the other radars, I would see this big bright white line up the middle here. But I would not, and a little bit of echo of this stuff out here. But I wouldn't see any of this other stuff. And so a lot of the sort of esoteric plasma physics that goes on and that I can sense with Arecibo, I can only sense with Arecibo. I can't see somewhere else. And that's driving new research in terms of the sort of basic plasma physics of what's going on. So up in the ionosphere, you have a unique plasma environment because it's a low-density plasma, but it's a plasma with no walls. So it's completely different from anything we can create in the laboratory, where we always have edge effects. In the ionosphere, we don't. So this is a uniquely important environment to us, and I'll show you what we're doing at Arecibo in a moment for that. That sensitivity enables us to make some really difficult observations. So the shape of the spectrum that is returned from the incoherent scatter signal depends on the ion composition of the target that we're looking at. So how much oxygen, how much hydrogen, how much helium, and so on. But in very subtle ways. And the Arecibo signal is so good that we're able to pick out, say, the proportion of helium even compared to hydrogen. And so these are daytime variations over daytime. Here's dawn coming up here. This is altitude, so we're going up to 1,500 kilometers in this case. And you can see big increases in the amount of helium in the atmosphere as we go through the night, and big variations at different times in the solar cycle. This is something where we don't understand what's going on, but this provides us with a unique view of the atmosphere that we can't get anywhere else at all. And that has some real relevance. So this is modeling results looking at what happens if the amount of greenhouse gas in the atmosphere goes up or down. And so this red line here shows what proportion of hydrogen we would expect in the atmosphere if we doubled the amount of greenhouse gas. And the dotted line is what happens if we halve the amount of greenhouse gas. So you can see that a radar like Arecibo, able to make these sorts of measurements in the upper parts of the ionosphere, is a very, very sensitive measure of what's happening with the greenhouse gas structure of the atmosphere. And so that's a lot of the sort of climate change, global change type study that is pursued by Arecibo and by the other incoherent scatter radars operated by the US and other countries. And here's just a little cartoon showing the radars that operated in the US. This is Poker Flat in Alaska. This is one of SRI's current frontline phased array incoherent scatter radars. We have another one actually operating at Resolute Bay in the north of Canada, but that came online after this was drawn. Here's Arecibo, of course. This is the Millstone Hill radar, which is over on the east coast. Here's the Sonderstrom radar in Greenland, which is also operated by SRI. And there's a big phased array radar at Yacamarca in Peru. And then the Europeans have some across the other side here, and there's a couple in Japan and in Russia also. There aren't so very many of them in the world. I mentioned the various optical instruments at Arecibo. So there's a whole optical facility up on the top of one of the hills beside the radar, with interferometers and with active LiDAR facilities, all looking at constituents of the atmosphere. And so they work together with the incoherent scatter radar. Actually, the weather in the vicinity of Arecibo isn't the greatest. There's a lot of cloud, and so we're busy currently relocating a lot of these instruments off to an island off the east coast of Arecibo, of Puerto Rico, to an island called Culebra, to come to a place with better viewing so that we can make observations over longer periods. But these things are very complementary instruments, so the total sort of view of Arecibo includes not only the big dish, but also these other things. I don't expect you to read all these words. Bob Kerr supplied me with this great long list of achievements, and I could stand here and read these and take up all evening, but I just pull a few things out that might be interesting that I hadn't mentioned before. So one from each decade, basically. So at 65, with the 430 megahertz radar, they were looking at Mercury and trying to determine the rotation rate of Mercury. It had been believed to be 88 days, and Arecibo was very quickly able to demonstrate it at much less than that. In 79, this was kind of amusing. In the atmosphere, you see big traveling buoyancy waves. They're called internal gravity waves. They're huge, long periods, up to several hours, 1,000 kilometers or more in wavelength. But a rather surprising one was detected in 1979, and ray tracing from that took it back to a point off the coast of South Africa, and it was believed to be the result of a nuclear test by Israel and South Africa. And it made the CBS News. A gentleman who did it was interviewed on air by Walter Cronkite. And the establishment said, no way. No, there was no explosion there, and basically rubbished what he was saying. But it was true. So Arecibo is a detector of nuclear explosions. 1980 is the first measurement of hydrogen escape flux from the planet. So we lose light elements out into space. They are the source of ionization in the magnetosphere. First measured from Arecibo. Something completely different. 1998, ESA, the European Space Agency, lost contact with the SOHO spacecraft. And actually, of course, it wasn't lost in the sense that we knew where it was, but they were able to determine exactly where it was such that ESA could actually re-establish communication with it, and SOHO is still working today. 2006, they started looking for water ice on the moon using the radar in connection with plans to put more permanent bases on the moon. Didn't find it. Most sensitive telescope, technically at the cutting edge. Structure's good for at least another 100 years, according to our civil engineering consultants. Lots to do, astronomy, planetary radar, whatever. However, some of you will have heard that yesterday morning we had an earthquake. There was an earthquake at 6.4 magnitude just off the coast of Puerto Rico, close to Arecibo. So we are currently closed down while we evaluate what happened. That's kind of bad for the observers, and we're probably going to have the visitor center closed for a day or two until we're sure everything's safe. We don't really like the idea of earthquakes. And then the future. I mentioned this business of using Arecibo because of its very detailed capability of observing plasma physics. So we are building at Arecibo a heater. So this is a very powerful continuous wave transmitter which can transmit at frequencies that resonate with parts of the ionosphere. And so this is actually 6 repurposed over-the-horizon radar transmitters, so they're very flexible transmitters. They're 100 kilowatts apiece, and we're going to use each of them to feed one part of a dipole, which we're placing into the bottom of the dish. So there will be 6 of these cross dipoles. I was trying to find a photograph that had a picture of a person in place so that you could have some view of the scale of this, and I couldn't find one. But this little platform down here, a person standing there would be about that high. So you get some notion of just how big these things are. Now, that's not really going to work because you get no gain from the dish just having these things in the bottom. And so we are going to have to put an extra subreflector into the dish. So here's the dish. Here's that suspended platform above it, and we're going to fly a mesh reflector underneath there, suspended off the towers. And so then in transmit mode with this heater, the transmission comes from the bottom of the dish here up to that subreflector, reflected down, illuminates the dish and goes off into space, enabling us to get some gain off the system. Now, a heater is a bit like your ability to deduce what's in an oil drum, by kicking it and listening to the noise. So this is a mechanism where you can go out and kick the ionosphere and see what it does. So normally, where we're making observations of the ionosphere, we can only make passive observations. What it does, and we can measure it. But with a heater, then we're able to make our own modifications and see what it does. And so that's a very powerful mechanism to move forward with our understanding of basic plasma physics. And we kind of expect that to come online sometime in the next few months. Arecibo has around 124 employees. There's about 100 of them involved with the operation of the system itself, and then the rest of them are involved with the visitor center because that's such a big deal, and we need a lot of guides and so on. So it's quite a labor-intensive operation. Now, a little sour note in all of this that the National Science Foundation Senior Review recommended some years ago that actually the astronomy part of the National Science Foundation should start to put its emphasis somewhere else and should begin to back off the amount of money that it paid into Arecibo. And that is hurting all of us today because we're operating with less money than there was a few years ago, and it keeps going down. So the funding profile used to be that there was a total of about 12 million a year available to operate the system, so in 2008, most of it coming from it to support astronomy, and some of it coming from the incurrent scatter side of the National Science Foundation. And the projection was that in 2014, these two would be equal, but there will be some money from NASA, but nevertheless, that comes out at a smaller number. Right now, today, these numbers are almost equal. So we're kind of holding our own, but it's becoming more and more difficult to find the money to operate. Nevertheless, there's a huge program still of all these radio astronomy programs that match very well with what NSF would like to do. So NSF needs more money. There's no two ways about it. We have 1 million infrastructure projects out there that we need to address together with this system. Everything from upgrading the system further to go to higher frequencies, to painting towers and cables and just everything. So there's a huge amount going on, a huge amount to do. Those 100 people who work there are incredibly busy and incredibly dedicated to do. There are a lot of plans for things for the future, everything from educational facilities based specifically at Arecibo, besides the sort of research that goes on and the PhDs and so on that are done by visiting scientists. There are plans for major upgrades to the facility, major rebuilds of the facility. This is AGMAS, is the Ana G. Mendez University System. They are the parent body of the Metropolitan University in San Juan, who are our partner along with the USRA, University Space Research Association, in running Arecibo. They have a plan for rebuilding. So this is in the area where I showed you those sort of Cold War era buildings that were the office blocks and the operations building. They have plans to build nice new facilities, new teaching facilities, a planetarium, a nice cafeteria and so on, and exploit and help increase that 100,000 visitors a year that we have there. Here's another view, and a whole new research building for our visitors and staff to work in. This is about a $50 million rebuild project, which would be wonderful to see come to fruition, but so far it's still just on paper. So we're trying to move with the times, and foster an environment that's good for the science and education and for the educational development of Puerto Rico. So we're increasingly tied into all of those things. Trying to keep on top of providing a scientific environment in which our users can get more Nobel Prizes, basically. I'll just go back to Bill Gordon. This is right at the beginning when they were starting this, when they wore bow ties to go to work. And he said, when we were talking about building this in the late 50s, we were told it couldn't be done. Imagine what people would say to you today if you said, I want to build a 1,000-foot dish. We were in a position of trying to do something that was impossible, but we were too young to know that we couldn't do it. I think that's pretty nice. So we're trying to sort of stick with that thing. We have challenges in the future operation of Arecibo, but we have huge amounts to do and huge opportunities, and so we're going to pretend that we don't know we can't do it. And just to go back to this business of the movies, because we came in that at the beginning, this is Jodie Foster and in Contact, which started the early part of the observation done at Arecibo. Just to round up, we have this wonderful visitor center, so next time you're in Puerto Rico, come visit. It's an amazing place, and it actually, pictures do it no credit. It's one of those things that you just can't get a feel for how big and impressive Arecibo is. One of my colleagues says that structure in the middle hangs in the air in exactly the way that bricks don't. And kind of that's right, it's just amazing. So do come visit. So that's what I was going to say. Thank you.